All right, so today is Wednesday, April the 8th. This is 504 Statistical Mechanics at the University of Illinois, and we are in the middle of doing diagrammatic perturbation theory. I put up on the slide here a Twitter that I made last year. I was teaching this class then. It was an evening makeup lecture, and this was a curve that was drawn on the blackboard when I got to class. So I thought it was pretty funny, so I added it to Twitter. And so yes, so you probably noticed that the technical difficulty and complication of what we're doing has significantly ramped up, and it will do so as we are doing these more complicated topics. However, the most important things for you to understand is what we're doing and why, and not necessarily the algebra. Okay, so let me put this away, and let me share from my iPad. Okay, so we've got the recording on. So let's just recap what we were doing at the end of last time. So what we did was we did diagrammatic perturbation theory of the partition function for a interacting gas, an interacting classical gas. And what we did after a large number of calculations, we eventually ended up simplifying everything by going to the grand canonical distribution and writing down the equation of state in terms of certain classes of diagram called cluster integrals that we defined last time. So and I showed you exactly why it was that the grand canonical distribution provided a very nice simplification and showed us that the grand partition function is simply the exponential of all the connected diagrams. So what we then ended last lecture doing was saying, well, what we're trying to understand is the pressure as a function of the density of a gas. And so what we have already from the calculation is the pressure in terms of the fugacity, lambda. And what we did was we said, well, I've got the constraint equation, which is also in terms of lambda. And so because of that, then we can write down that the pressure is simply then a function of the fugacity, the number density is a function of the fugacity, and therefore if we can simply just eliminate lambda between these equations, then we'll get exactly what we want. We will get the equation of state as a function of density. And I pointed out that that was not correct and not going to work. And the reason it isn't going to work is that the cluster integrals are functions not just of temperature, but they also depend on the volume. And so that means that when we invert the number constraint equation, what we're going to get is a function that depends on the volume as well as the density. And so therefore we can't simply eliminate lambda and get pressure as a function of n. And so what we ended by doing was saying, well, fine, but we constructed the cluster integrals in such a way that the thermodynamic limit exists. And so we took the thermodynamic limit, we take the limit v goes to infinity, n going to n over v staying fixed, and that removes the v problem, and then we can simply do the inversion. And now this time what we have is that the cluster integrals are replaced by the v goes to infinity limit of the cluster integrals, and so then everything should work out fine. So we're going to go ahead now and do that. We're going to do the calculation and find out how things work. Now, before we get started, how is the sound quality? Is the sound quality good? Okay, thank you. And is it better now or is it worse? So I'm using a different microphone. there's some background hiss. Okay, so I'll put it back to where it was before, which is using the laptop microphone. Okay, so thank you very much for the feedback. Sometimes on different calls, different microphones work better. Okie doke. So let's write down the virial expansion in the following way. So I'm going to write it as follows: PV over KBT. And this V, excuse me, this V is meant to be little v, where little v is defined to be big V over n, the volume per particle. So PV over KBT is then 1 plus V2n plus B3n cubed plus ... and that's defining for us the cluster expansion. Sorry, the virial expansion. So these terms here are the virial coefficients. So let's then ask ourselves the following question: what is the small parameter in this expansion? And we kind of already know the answer, because we know that we are really doing an expansion about a very dilute case, and then as you increase the density, the number of two-body interactions increases. So what we're going to do is the strategy is going to be to insert this into the equation of state and equate terms and terms. But what the small parameter is, we can see from the following consideration. If we look at the cluster integrals b lambda slash, so they depend on the thermal de Broglie wavelength, lambda t. And if you look at how we defined that, we can actually see how many powers of the thermal de Broglie wavelength they involve, because of the number of integrals involved in the BLs. So from the number of integrals, in BL, we can see that in fact these virial coefficients B sub L will be lambda t cubed to the power L minus 1 times another term, which I'm going to call little a, and that term will also depend on t. So that's going to be the that's how I'm going to rewrite the B's to take out all the thermal de Broglie wavelength. And so what that means is that PV little v over KBT, I can write as the following: it's the sum from L is equal to 1 to infinity, these sort of modified virial coefficients A sub L times lambda t cubed over the volume per particle raised to the power L minus 1. And so the point is that this quantity over here is a dimensionless expansion parameter. Because it's just the ratio of two volumes. So okay, so this is great. So now we have the expression for PV over KT, but we also know that that P and 1 over V itself have these expansions. So over here on the left, P is equal to this, V is equal to this, and so this whole formula can be written as the ratio of one of these expansions over the other. So substituting in for P and for V, we have the following, the sum from L equals 1 to infinity of B slash L lambda to the L, and that's divided by the sum from L equals 1 to infinity of L B slash L times lambda to the L. So these things, so PV is equal to this, that's the thing that we want, and it's also equal to the ratio of this term and this term, and so we just write that ratio like this. So what you have here is on the left-hand side, you have an expansion powers of L, and on the right-hand side, you also have an expansion in powers of L. And so what the strategy is going to be is to equate those powers of L and see what we get. So let's put this all together. So so I can equate these expressions. And the other thing I want to put in is the fact that that v, that 1 over v, or lambda t cubed over little v, is also equal to the sum from L equals 1 to infinity of L BL slash lambda to the L. And why do I care about that? Well, I care about that because we're going to put that into this formula over here. So there on the left-hand side, you can see that we also have an expansion in powers of L. So what I have then is a very complicated expansion of expansions. And let me write it out in detail. So for all values of L, all values of lambda, what we get is this really weird formula. Sum over L from 1 to infinity, A sub L. Now we're going to put in the virial term over here. So that virial term is 1 over V, which I'm going to write down now with a dummy variable, little m, just to make sure we don't get confused. M B sub m, lambda to the m. So that's my formula for 1 over V, and I have to raise that to the power L minus 1. And then that thing is equal to the ratio of P over 1 over V, so that's equal to the sum from L equals 1 to infinity BL slash lambda to the L divided by the sum of L equals 1 to infinity of L BL slash lambda to the L. Okay, so this thing has to be true for all values of L, of lambda. And so what we do is we now equate powers of lambda on both sides of this formula. And you can see that it's really terrible because I've got a power series expansion of a power series expansion, and then I have a ratio of 2 power series expansion. So there's a huge number of terms and things that are going to come out when this works out, and I'm only going to work out the first few. So let's start doing that. So let's multiply by this denominator. So we're going to take this term and put that over here. And so let me write down the terms that we get. So it's going to look something like this. So A1 plus A2 times the sum from m equals 1 to infinity of m bm slash lambda to the m plus A3, that same sum, m equals 1 to infinity m bm lambda to the m, and now that's going to be raised to the 2 power plus dot 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 multiplied by the sum, and let's call the dummy variable L. L equals 1 to infinity of L BL slash lambda to the L. So that thing is equal to the right-hand side, and the right-hand side is just L equals 1 to infinity BL slash lambda to the L. Okay, so that's an awful equation. And now all I have to do is equate powers of lambda . And what I get out of that is I'm going to get an expression for the A sub L's, which are basically the virial coefficients, in terms of L clusters. So what do we actually get when we do that? So I'm just going to save you the work. So we get A1 is just equal to B1, and that is equal to unity, so nothing special there. A2 turns out to be minus B2 slash, and that's in fact in agreement with what we've already seen. And then I'll write, I'll write this down on a new page. And then over here, A3 is more complicated. It's this 4B2 squared minus 2B3 slash. And when you work out what those things are, what you will find is it's minus 1 over 3 lambda t to the 6th power times the integral from 0 to infinity f12, f13, f23, d3 r12, d3 r13. So it turns out to be just one single integral. And then if I go to work out A4, I'm just going to write down what the thing is. It's minus 20 B2 cubed plus 18 B2 B3 minus 3 B4. And that also has a simplification. But I'm not going to go into that in particular. So let's just look at A3. And in fact, what you can see is that this is just a diagram, apart from the factor of lambda to the 6. This is just a diagram that looks like this. So it's a particular diagram. It could have been any of the three-body diagrams, or the three-body diagrams, but it turned out just to be this one. So it's this, and not a set of different diagrams. So in other words, what's happened is there's been some miraculous cancellations. And the miraculous cancellations lead to the fact that the virial coefficients are just involving so-called irreducible cluster diagrams, cluster integrals. So now I've only demonstrated this to you for the second and third virial coefficients, but it's true for all orders, and how to do that is quite complicated. So let me define what I mean by an irreducible cluster integral. So irreducible L clusters are L particle graphs where there are at least two independent non-intersecting paths that link each pair of particles. So if I were to look at, say, this diagram, this one is reducible, but this one is irreducible. And it's irreducible because I can simply go from, I can go, if I want to go from here to here, I can go like this, or I can go like this, and the same thing for all of the others. So these are these irreducible diagrams. Okay, so this is the miracle that I haven't proved it to you to all orders in perturbation theory. We'll just take it for granted. So, but it is true. So now, if we define, so what we're going to do is we're going to define beta sub L to be a kind of special kind of L cluster. So we're going to define it as this. We're going to take the limit as v goes to infinity. We're going to take these prefactors. So this is L minus 1 factorial lambda t to the power 3L minus 1, and then normalize by the v. So this is just like the prefactor we had for the L clusters. And now what we're going to do is we're going to define it to be the sum of all irreducible L clusters. So that's that's the quantity beta, and then what you can show is that it turns out that to any order, these Virial coefficients take with a thermal de Broglie wavelength factor taken out, the A sub L's as just minus L minus 1 over L times beta L. So now, in fact, we have another simplification. It's not just that we have the linked cluster theorem, we also have this theorem, which tells us that, in fact, the only diagrams that we need to calculate are the irreducible L clusters. Okay, now that doesn't mean that they're easy, though. They're very hard to do, and so now let's go on to see how well it works. So let's suppose we ask, can we calculate these things analytically? And the answer is no, obviously we cannot. But for, if we say that the potential, so the answer is no, at least for a realistic potential. If we have hard spheres, we can do something. So a hard sphere has the potential U is equal to infinity if R is less than R naught, and it's equal to 0 if R is greater than R0. So that's what we call a hardcore potential. So then the Virial coefficients up to B7, so we can compute B2 all the way up to B7, those can be done analytically, although it's not pretty. And in some cases, you have to do some numerical integration at the end. So you can reduce them fairly well. If I have a Lennard-Jones 612 potential, we can compute them. So let's have a look then at what the results look like. So over here, what I'm going to plot is the number density multiplied by the diameter cubed. So that's an integer, and up here PV over NKVT. So again, that's, I said this was an integer, but what I meant was it's just a pure number. So let me plot the curves you get. So this is going to go up to 6. This goes up to about 12. This goes up to about 1, something like that. So if you compute up to B2, you get a curve that looks like this, as this is just using B2. If on the other hand, I add the B4, what happens is it goes along like this and then deviates at higher densities. So I get something that looks roughly like that. If I go up to B6, it goes along this curve and then eventually deviates. So I get something like that. And if I plot the actual, what the data looks like, the data looks something like this. And so we see that the diagrammatic perturbation theory gives a reasonable result as long as the density is not too high. Okay, so what about the critical point? So as we go up to higher and higher densities, eventually the gas will turn into liquid. And as we go to higher densities, the gas will turn into a liquid. And we can estimate the critical point by which it does that. So let me explain to you what I mean by a critical point. So let's see this. What I want to do now is I want to talk a little bit about the phase diagram of a fluid. Okay, so let's draw the axes. So the usual way that we think about the phase diagram of a fluid is we think about it in the pressure, temperature phase plane like this, and the variables that we're going to consider are what happens as we increase the pressure. So what's going to happen is we're going to find that there's 3 lines in this diagram. So let me draw them like this. So roughly speaking, they follow this kind of curve. So this phase here at high temperatures and low pressure, that phase is obviously going to be a gas phase. If I take a gas and I increase the pressure, what I'm going to get is, of course, a liquid. And if I take a liquid and compress it, or I cool it down, then what I'm going to get is going to be a solid. So that's the phase diagram of the usual matter. This point over here, where things end, that's called a critical point. So what you can see is that the phase diagram, which I'm drawing, the phase boundary between liquid and gas ends at this critical point. So what that means is that it's topologically possible to go from liquid to gas without having to go through a phase transition, and we'll talk about that in a little bit. Then the other thing is, what I've drawn over here is there's a junction here. At this junction, we have the gas, liquid, and solid phase are all together. So this is called a triple point. And then lastly, what I've drawn is an arrow on this thing over here, and that indicates that there is always a transition between fluid and solid. And the reasons for that come from symmetry, and we may talk about why that is in a little bit. So unlike the liquid-gas transition, which ends at this critical point, the liquid or gas solid transition keeps on going. So maybe I'll just make a note of that. So the liquid gas transition doesn't exist above Tc. So here is Tc, that's this temperature here. It doesn't exist above Tc, but the fluid, and by fluid I mean either liquid or gas, to solid transition always has a transition, always exists. So, and the reason for that is basically that liquid and gas have the same symmetry. But a fluid and a solid have different symmetries. And that's not a very trivial point to see. If I told you, if I talked about, say, a fluid and a crystal, you would say, well, they obviously have different symmetries because a fluid is translational invariant and a crystal has broken translational invariance. But a disordered solid, such as a glass, would also seem to have translational invariance. So exactly what the symmetries are is quite complicated and not as trivial as it might seem. So we're not going to spend much time talking about that, but we will get to that. Okay, so that's the phase diagram in the pressure temperature plane, but we also need the phase diagram in the pressure volume plane. And then we're going to do that at fixed temperature. So let's go to another blackboard and let's draw what that looks like. So this axis is the volume, this axis is the pressure. So let's draw what we think is going to happen for a fluid at very high temperatures. So at very high temperatures, well, we'd expect the fluid to basically look like an ideal gas. So the ideal gas law is PV equals KT. KT is going to be a constant. And so what that says is that P goes like 1 over V, which is a hyperbola. So the equation of state is going to look something like that. So I'm going to have some lines that go like this. Now what's going to happen is as I go to lower and lower temperatures, what's going to happen is I'm going to draw it, and then I'm going to show you why it looks like this. So it looks something like that. And then when I draw these graphs, I always end up messing them up. So something like this. Okay, so let me draw in here. I can see that this is already going to be a bit of a mess. Let me draw in here I'm going to erase this graph here. Let's erase that one and let's draw it like this. Ah, oh yeah, start again. Okay, something like that. Okay, so these curves here, these ones along above here, these are for T greater than TC. This one over here is T equals TC. It just equals this this line here, and this point is critical volume, and this point here is the critical pressure. And then these curves over here, these ones are for T less than TC. So what's happening is this, and this flat region here is two-phase coexistence. And so I want to explain to you what that is and why the curves look like this. So to do that, let's think about the following series of experiments. I'm going to take a system, which is a container, which has in it some fluid, and it has a piston on the top. And this thing here is a heater, and this thing here keeps the system at constant temperature. So something like that. And now what's going to happen is inside I have a bunch of gas particles, so they're just floating around like that. And so what happens is in this region here, if I now were to take the system and now push the piston in, so now I'm going to push the piston down to here. This is the heater. So now what's happened is the gas has got a much higher density. And so what's happening is, of course, as I push it down, the volume has decreased, and therefore the pressure has increased. So this picture here, let's call this picture 1, might be at this point over here. And then let's call this one picture number 2. So that means that we are somewhere up here. Oops. Yeah, somewhere up here. Okay, great. So now let's imagine what happens as we compress it even further. So now we've compressed it down to here. So as we're compressing it, keeping the thing at constant temperature, so what's going to happen is now as we the fluid has done the following thing. I've compressed it so much that some of it has started to become liquid. So what I have down here at the bottom is the fluid in liquid, and because the liquid is denser, it falls to the bottom of the container. So liquid is always blue, and then above the liquid is the gas, just like floating around, just as we had before. So this picture here, we'll call this one a number 3, and that would be somewhere, let's say, along here. So what happened is now I'm in the presence of gravity. So there's gravity. So the liquid has fallen to the bottom, and now I have two-phase coexistence. So now what I do is I squash it even further. Like so. And now what's happened is essentially all okay, everybody hear me okay? Something weird happened. I don't know what. We got disconnected. So we're still recording. Okay, good. So now what's happened, thank you. So now what's happened is that everything in the fluid has turned into liquid. So let's call this situation number 4. And so that would be somewhere, let's say, just right over here. And now what's going to happen is this: if we compress even further, then what we're going to do is we're compressing just the liquid. And in a gas, the atoms are far apart. In a liquid, of course, they're bumping up against each other. And so what that means is that it requires much more force to compress a liquid. Because the atoms are so close together. And that means that the P as a function of V curve rises much more steeply. And that will be in region, whoops, wrong color. That'll be in region 5. And here is region 5. Whoops, region 5 is up here. So that's the anatomy of the phase diagram. And so this point up here, this is the critical point. And we can see that if you're at the critical point, then it's a point of inflection. For P as a function of V. And so what that means is that at that point, dP by dV is equal to 0, and d2P by dV squared is equal to 0. And both of these derivatives are taken at fixed temperature, and that temperature has to be the critical point. And so, so what you can do is we can estimate this from the virial expansion. So what did it turn out to be? Well, let me give you some example. So the example I'm going to use is the Leonard-Jones 612 potential that we talked about. So for the Leonard-Jones 612 potential, I'm going to draw here the virial coefficient that you can compute. And then on this axis, the critical temperature, and that critical temperature, we'll write it in units of kBTC over epsilon, which is the binding energy. So this turns out to be quite insightful. So we find that for B3, this number is 1.445. For B4, we can do that, it's 1.300 ... And for B5, it's 1.291. So those are the predictions that you get from the virial coefficient. And if you take argon, which we know is well described by a Leonard-Jones 6 potential, so we know epsilon, we know R naught for that, and so then you can get that kBTC over epsilon is 1.26. So what you can see is that the virial expansion is converging to the correct result. And is accurate up to about something like 2%, something like that. Okay, so that's all that work that we've done. It just tells us about what's happening in the upper part of this curve over here. So in this region up here, in this region, this is where diagrammatic perturbation theory is okay. And but we want to do more than that. We want to understand the whole phase diagram. So after, essentially, what do we learn after all this work? We got a decent approximation to the easy part of the problem. So let's now ask the following question. Well, what we really would like to understand is the strongly interacting part of the problem. That's the liquid state. And so now I want to talk about liquid state theory. So the thing we want to go on to next is a strongly interacting part of the system. And so part 5 is on liquid state theory. All right. So what we're going to see in this section is we're going to look at understand the limitations of diagrammatic perturbation theory. So we're going to see when it works, and we're going to see that it really breaks down in the liquid state. because everything is so strongly interacting. So then we need to figure out, well, what do we do in a strongly interacting state? And so what we're going to see is some understanding of what methods we can use for strongly interacting problems. So that's what we're going to do next. So let's first of all take a look at why we expect the diagrammatic perturbation theory to break down. So the next thing we're going to discuss then is the breakdown of the virial expansion. And we're going to look at its breakdown in the liquid state. Okay, so to do that, we're going to look at what the virial coefficients are related to in terms of the f functions. So here's the basic idea. So the basic idea is this: we know that the virial coefficients, the bn's, they are related to those irreducible cluster integrals, which we called beta n, and these beta n, if they related to the L clusters and so on. So these are basically some integrals of the f functions that we started with. And those f functions, what was special about those f functions was that they were basically zero unless you were very close within 1 or 2 atomic radii. So these f functions were constructed. Remember that these were e to the minus beta u minus 1. That's how we defined these f functions. And these then had the property that these were basically very small, unless the particles are close, within 1 or 2 atomic radii. So that was the whole point about the f functions. So what that means is that when I look at these betas, these irreducible L clusters, these are going to be essentially their integrands are going to be 0 unless n minus 1 particles are close together. So what that means is that if I look at the integrand in the terms in beta sub n, they're always going to be small, what r is, unless how many particles are in beta n? Well, there's n, so there's n minus 1 particles are within 1 or 2 atomic radii of the test particle, of the particle 1. So that means then that when we evaluate these beta n's, just by this sort of scaling argument, we expect that beta n is going to be the volume of an atom, maybe it's multiplied by a factor of 1 or 2, raised to the power n minus 1. Okay, so that gives us some kind of estimate of what these irreducible cluster integrals are going to look like. So now let's plug that in to the virial expansion to see what the virial expansion is really an expansion in terms of. So let's write it down like this. PV over KBT, PV over KBT is equal to 1 plus B2, 1 over V, plus B3, 1 over V squared. Actually, I should really write it like this, shouldn't I? Something like that, and so on and so forth. And I can write this as, why not just write down what the general term is here. So this will be Bn times 1 over V to the power n minus 1. So if I write this all down, yeah, so this is going to then be the following. It's going to be 1 plus, I'm going to write that the B's are, so yeah, so what I'm going to write is this. I'm going to write down that B n is defined to be alpha n times V atom to the power n minus 1. So I'm going to make that definition. Then when I go back to the virial expansion, my terms are going to be alpha 2 times V atom over the volume per particle plus alpha 3 V atom over volume per particle squared plus and so on for higher orders. So what you can see then is that the expansion parameter in the virial expansion is this thing here. And so what you may say then is that the terms, in order for this expansion to decrease, what we need is that V should be much greater than this, or V should be greater than this, for the terms in the expansion to actually decrease. So why do we say that? Well, the terms are, we can think of this as being some small parameter, let's call it epsilon. So this is of order epsilon, epsilon squared, epsilon to the n minus 1, and so on and so forth. And so if any expansion in a small parameter epsilon is only going to converge if epsilon is smaller than 1. And so therefore we need V atom over V to be smaller than 1. Okay, so that's going to be a condition on whether it converges or not. But really, the question is how quickly does it converge, if it actually does at all. So let's discuss that. So what do we learn from this? As we increase the density, and therefore decrease the volume per particle V, the epsilon, which is V over V atom, is getting larger. So that's a big problem. And so what that means is that the important clusters are not just 2 clusters or 3 clusters like we had when we were looking at low density, but n clusters, where n is all the particles in the system. at high densities. So what that basically means is that the whole system is one big cluster. So if the whole system is one big cluster, then that means that perturbing about an ideal gas is going to be a very poor approximation. And so that means that we should expect that something will happen there. So between the low density case where the cluster expansion works and the high density case where everything is one cluster, it's not surprising that there is some kind of phase transition in between. So that suggests that there's a phase transition between the gas and the liquid phase. So they don't have to be different phases, but you can always have a phase transition between them. In the picture that I showed you of the phase diagram, going back to here, going back to this phase diagram. So one thing I want you to notice is that if I start off here in the gas phase, if I go up in this way to liquid phase, just by increasing the pressure, I will of course run into a phase transition. But there's nothing to stop me raising the temperature, then raising the pressure, and then lowering the temperature like that. And if I do that, then I will have got from a gas to liquid without going through a phase transition. So phases don't really exist, they're not topologically distinct, but the phase transition itself is some kind of non-analyticity in this phase diagram. Okay, so this suggests that there is a phase transition. There's another point that I want to make. So let's suppose, so a second point. So the question is this: if this parameter epsilon is less than 1, well, let's just write it as less than rather than less than, much less than. So if this is less than 1, does that imply that the series converges? So the answer is not necessarily. So the answer is no. Even if epsilon is less than 1, that is not a necessary a condition, or that's not a sufficient condition for convergence. But so that's just speaking mathematically. However, it does turn out that there is a finite radius of convergence. And I don't remember actually whether that's true for the hard sphere or the Leonard-Jones. I forgot to write that down. So what that means is that we're in an interesting situation. So what this says is that liquid state theory is hard because there is no small parameter. So that means that we don't know how to proceed systematically. So you can't use diagrammatic perturbation theory because the terms in the diagrams, they're all of the same order of magnitude. So when epsilon is order 1, all terms in perturbation theory are important. So perturbation theory is really not much use. There's other problems where perturbation theory is not useful, and those are the hardest problems in physics. They're problems like critical phenomena, like fluid turbulence. All strongly interacting systems have this difficulty that we don't have a small parameter, and so it's hard to proceed. So then you might say, well, how do we proceed? So this is obviously a huge and generic problem, and so I'm going to show you some ways to make progress. So the answer is that we can make progress by solving for the 2-point correlation functions in a self-consistent way rather than an exact way. So self-consistent might work, but it may be wrong. So somebody has a question. Is there a liquid-gas phase transition in a system of hard spheres? So yeah, good question. I didn't think so. Yeah, I don't think so, but I think the answer is complicated. Let me give you a better answer next time, because I want to make sure I don't tell you something that's complete rubbish. You might think that there wouldn't be because there's no attractive interactions. So you'd say, how can they be a liquid? There's no surface tension. But I think it depends on what you hold constant. So as you put more hard particles into a system, they can become jammed in that system. Well, that's obvious. So there's a finite density that you can put in. So you can get some kind of phase diagram. But let me get back to you on that for next time, or send me an email and I'll answer to the class in email. Yeah, so that's a good question. So let me go on and talk about self-consistency. The self-consistency, I'll explain what I mean for that. Self-consistent can be wrong or right. You can be self-consistently wrong. So just being self-consistent is not the same thing as solving the problem. And the other thing that we're going to see about self-consistency is that it's often associated with mean field solutions. And what I mean by mean field theory is that we ignore fluctuations. And where that comes into play, in particular, is in the theory of phase transitions. So we'll say something about that, not today, but in the next section. Okay, so let's just go through the basic idea. So the basic idea is this: if I write down the equation of state, so PV over NKBT, so what we saw a few days ago was that we can write down the equation of state in terms of an exact expression, in terms of the two-point correlation function. So we saw that. And so what I'm going to show you now is something very interesting. What I'm going to show you is that there is an exact formula for this. So you may say, great, there's an exact formula for the two-point correlation function. So in that case, why don't we just calculate that? And then that's in fact what we did with the heuristic approximation. With our heuristic approximation, we calculated G of R, and we had some simple formula for it, and then we just plugged that into the equation of state. So there is an exact formula for G of R. So and G of R is a two-point correlation function. But the problem is that that exact formula involves the three-point correlation function. So, but so we can put a little subscript 2 on this to tell you it's a pair or two-point correlation function. So that involves the three-point correlation function, D3. So you may say, fine, well, just go ahead and calculate the three-point correlation function. But then what you're going to find is that G3 is you can get an exact equation for G3, but that involves the four-point correlation function. And then the four-point correlation function is a function of the five-point correlation function, etc., etc., etc. And this thing is called the BBGKY hierarchy. So this is Bjorn, Bogolyubov, BBG, Green, Kirkwood, Yvonne hierarchy. BBGKY. And there's so many people whose names are associated with this, and there's almost surely many more that were omitted from this. So anyway, this is the BBGKY hierarchy, and what this is, it's an exact formula which we'll talk about, and it always exists. This thing always occurs in many body theory. So here I'm going to show it to you for the classical gas, but it also occurs in quantum field theory, it occurs in fluid mechanics and turbulence, it occurs in electronic many-body theory. It always occurs in many-body theory descriptions of matter. And so on. So let's start what it is. Let's start by defining. We're not going to get into it too deeply today, but let me start by defining higher order correlation functions. So let's do it in the following way. So I'm going to talk about functions like this. So I'm going to call row 1. I'm going to define row 1 of x to be the following. It's simply, I take the sum from I equals 1 to n, the expectation value of x minus I. Okay, so in this formula here, you tell me what x is. That's the thing that goes in there. And then I find out how many particles are at that point in space, and then I do a thermal average. And so this thing is really just another name for the particle density. Okay, then I can define row 2. So that's going to have two variables, x1 and x2. And so that we're going to define like this. I'm going to sum over all particles, but not I equal to j. And then delta of x1 minus Ri, delta x2 minus Rj. Like that. Yeah, need a mess there. Okay, so now what I do is you tell me what is the value of x1 that you want, the value of x2 that you want. Those are those numbers here. So basically this is telling you what is the probability of simultaneously finding a particle at x1 and a particle at x2. And, or if you like, two particles separated by the distance x1 minus x2. So the I and the j that come in here, those are just dummy variables. You just sum over those, and then you get this number. And you can keep doing this for 3 bodies and so on. So you can get row 3, row 4, and so on and so forth. And when I write down what this average is, what do I mean? Well, what I mean is I'm integrating over whatever is inside the brackets times the probability of finding a particle as R1, particle as R2, particle at Rn, product over I T3Ri, and then normalized by the integral of P T3Ri. Okay, so that is that is how we define higher order correlation functions, and we also know that the system is translationally invariant. So the system is translationally invariant, so there's a bit of a simplification. So what does that mean? Translational invariance means if I take the Hamiltonian of the system, I have a bunch of particles whose positions are Ri, and now I add to the particle positions some fixed vector. I just take my system and just move it to the left, to the right. Then what I get is something that doesn't change, and so the Hamiltonian is the same. So that's what we mean by translational invariance. And so what that means is that the row of x is just going to be independent of x. It's going to be n over v, which is just the particle number. If I take the 2-point correlation function, so it depends on 2 points. Well, what do I expect to happen? Well, you might say, well, if the particles were not interacting, this would just be particle 1 times particle 2 divided by the volume squared. And so this thing would be just basically going like n squared. So that would be true. Of course, it's not true if they're interacting, but it is true if I take the limit of x1 and x2 being very far apart. So if they're very far apart, then the 2-point correlation function is going to factorize. And so row 2 of x1 and x2 goes to row 1 squared in the limit as x1 minus x2 goes to infinity. And so you can see then that we can normalize these higher order correlation functions. So this suggests that we normalize in the following way. So we say row 2 of x1 and x2 is then just equal to n squared times g of x1 minus x2. And that this g here is really, this is the same thing as the pair distribution function that we talked about already. Okay, so that's the so that's how we define these G2s and G3s. So we're going to stop there. So next week, we're going to derive the exact equations that relate G2 to G3 and so on and so forth. And we'll see how we can get an exact set of equations. And so that's the first thing we're going to do. And then we're going to find, I'm going to show you what we call a closure approximation. And what is the closure approximation? Well, I told you that over here we have a system of equations which is G3 in terms of G4, G4 in terms of G5. And so we think of these equations as an infinite. Wow, that's really not good. Try it again. And because there's an infinite set, we say that they're not closed. So what we're going to see is that the idea of a closure approximation is an extra assumption that we can use to close the hierarchy. And where that extra assumption comes from is, well, you just wake up one morning and say, I think this is what should be done. And so we'll talk a little bit about that. Okay, so that's the end of today's lecture. So have a good rest of the week. And I'm going to stop the recording right now, and then we can take any questions.